Hello, and welcome to BCG's Sustainable Soils Discussion Panel. Today I'm being joined by industry that together have around about 80 years worth of experience focused on soil health, soil fertility and soil carbon. Recently, initiatives and investments from various funding bodies and government departments are taking a particular focus on soil, such as the National Soil Strategy that's recently been announced by the government. So BCG, with funding from the National Land Care Programs, Smart Farm Small Grant Scheme, have organised this to provide growers with some more information in relation to medium rainfall broadacre cropping regions of South Victoria and South Australia, and an opportunity to learn more about sustainable soil management and build high performance. The leader of our discussion today is Dr. Cassandra Schefe. Dr. Schafe's career started in agriculture Victoria, where she was first employed as a DPI cadet in 1996 while studying agricultural science. She then became a research scientist in soil chemistry before moving to the Riverine Plains Farming Group based in Yarrawonga and starting her own private consultancy. Through her private consultancy, Dr. Schefe works with universities, councils, cattle management authorities, industries, farmers and other organisations for science advice. Cassie's work has helped on improving the long-term productivity and quality of broadacre cropping systems in New South Wales using low carbon management practices. How are you today, Cass?
Ripper today, Tom. Ready to roll.
No problems at all. So alongside Cassie, we've got Dr. Rob Norton, who's kindly joined our panel of experts. And Rob has an experience in crop nutrition, farming systems and agronomy. And for the past 40 years has worked in education, training and research for the Australian grains industry and various funding organisations, including the University of Melbourne and Longanong College, where he actually lectured my own father. How are you today, Rob?
Yeah, I am old, but yeah, he's done well to train a young man like you, Tom. So good morning.
So Rob's a regular speaker at industry conferences and national and international science forums, and he's authored over 150 science-based publications, as well as many more articles for the industry. So we're really lucky to have Rob with us today. And finally, we've got Dr. Amanda Schapel, a senior consultant for the Department of Primary Industries and Regions in South Australia, who's worked on agricultural soils since 1997. Amanda started her career classifying and assessing soils for horticulture development, but in the last decade has focused on the importance of organic carbon, particularly in broadacre sandy soils. Amanda has been involved in several carbon projects, most recently benchmarking soil carbon in South Australian agricultural soils under a range of soil types and management practices. So this is the first part of our two-part series on sustainable soils, which is being recorded today and has a focus on the principles and limiting factors for soil management, a base from which we will build the discussion on practical management strategies for building high-performance soils. So I'll hand over to Cassie Schefe now, who's going to lead our discussion and sit in the background and take questions as needed. So anyone in the audience today who'd like to raise their hand using the functions on Zoom can do so, and we'll get around to answering your questions either during the discussion piece at the start or in a Q&A session at the end.
Thank you, Tom. So yeah, just to reinforce today, we'd like to be quite informal and really want you to get out of it what you need. So if there's anything that we talk about today that you're not think quite hits the mark or you want to delve into a bit more, please let us know and we'll come back to that in the second part of the series and make sure that we really cover off on what you need. So yeah, the presentation this morning will be quite informal, and I'll invite Rob and Amanda to join me through the presentation to bring further discussion and insights into what we're talking about. So this morning really is around a lot of the principles and the basic factors which govern carbon in soils and everything that engages with it in that environment. So we're not going to delve into the specifics around each soil type and each specific farming practice this morning. What we'll plan to do is, if we can build kind of the basic building blocks and get all the fundamental connections right, then in the next session, we'll then build on that in terms of the real practical applications and activities and strategies that you can use on farm. So we'll think of this as like the theory kind of aspect, and then next presentation will be all around the rolling up our sleeves and getting some nuts and bolts happening. So before we start, this is just something that I'm particularly really passionate about, is the fact that farmers really get the raw end of the deal when it comes to a lot of the discussion around soil carbon in popular press. So there's a lot of a lot of focus on, from people who really don't understand the mechanics of what soil carbon is and how it's done, is there's, I don't know how many times I've read on social media stuff, oh, if farmers only knew how good soil organic matter was, if they only knew how wonderful carbon was, they would be increasing it, and they can have so much impact on climate change and on the world. It's all around, if they, all you have to do is increase carbon. That's, how hard can that be? And so there's this real emphasis in a lot of the messages coming through that if you, as in the farmer, increase soil carbon, then good things will happen. So it really takes carbon as that starting point. So all we have to do is increase that, and then, it's all wonderful. So when we talk about good things in that context, we're really talking about, reducing atmospheric CO2, greater biological activity, nutrient cycling, water retention, but some really big picture things. But the challenge is that there's only so much that farmers can influence. And so let's look at what's in their control and what you can do within your farms to actually work on carbon. But a key thing is that we need to look at things from a different perspective. We need to flip that whole aspect to say, if you do good things, then carbon might happen. So the key aspect is that we're really looking at carbon as an end result, or as what happens when you do something, not if we increase carbon, then things happen. So it really needs to shift that dial a bit. And when we talk about good things in this context, we're really talking about those management options that you have control of that have a range of productivity and profitability benefits. So they're good things to do anyway. They're also good for carbon. So when we think about that, we really look at what's within your sphere of influence, as I mentioned. So things like ground cover, fertility, deep-rooted perennials in our pastures, diversity in our cropping systems, and fundamentally addressing our soil constraints. And we'll go through all these in more detail this morning. And within those practices, then if everything's set up well, then soil carbon and soil organic matter kind of flow from there. Then you worry about, then there's all these downstream benefits that cannot be directly influenced by farmers, but are of value in the bigger picture of life. But really, when you think about it, there is so much that you need to do and manage within your farming systems. There's so much complexity that you're dealing with. I think you've probably got enough on your plate without worrying about how you can influence the state of the world. So let's focus on what's within your sphere. So this morning, we'll talk about the commonalities between productivity and soil carbon. We'll talk about what's the most limiting factors in your system. We'll connect soil carbon and soil fertility, and then we'll move into some comments around if you don't measure it, then you can't manage it. So it's not, if we don't have some numbers and an idea of the state of play and how things are moving, then you can't really make good decisions to improve that. So a key aspect which tends to kind of get dropped off a bit is that you don't have to make a choice between managing for productivity and managing for soil carbon. So we know that what's good for the plant is obviously good for productivity, and that's also good for carbon. It's not a mutually exclusive kind of thing about saying I'm carbon farming or I need to focus on carbon. Because end of the day, and we'll go through this a bit more, you need plants to generate that root material and the plant litter, which then forms the basis of organic carbon. So something to consider is that both plants and organic carbon will grow in our soils and perform up to the threshold of whatever is the most limiting factor in that system. Rob, Amanda, any comments at this point?
I think they're great points. I think the focus on what you can do yourself rather than what is carbon is great.
Perhaps, Amanda, when people get their soil test back, they get soil organic carbon measured, and they also get soil organic matter. So I know a bit later in your talk you're going to describe some of the relationships there, but But what is, do you want to explain maybe a little bit more about what organic carbon and how it relates to organic matter? Because sometimes the tests aren't necessarily measuring the same thing.
Should we pause that, Rob, till we get to the slide with that detail, and then we can expand that further?
Sure.
But yep. Amanda, if there's anything that you'd like to add at the moment, certainly happy. No? Okay. So let's take it right back to this whole complete connection between plants and organic carbon. So we know that the way carbon gets into soils isn't some kind of magic brew that's applied, or a kind of a fairy dust that's put on and then grows carbon in our systems. It's fundamentally through the conversion of CO2 in the atmosphere through the plant, through photosynthesis, which then captures that carbon from that CO2 into carbohydrates and other structures within the plant. Then when the plant dies, the microbes in the soil break down that organic matter. Then when the microbes die, then they're decomposed by other microbes. And through that whole cycling process, that's where you get the net accumulation of carbon in the soil. So I said a net accumulation. So if there's a net accumulation of carbon through this process, then we can say that the carbon from the atmosphere, so the CO2, as it moves through the plant into the soil, is captured or sequestered into soil. So that's really the fundamental process of carbon sequestration. So the key thing is around that net accumulation. Because it seems like a really simple process. You grow plants, then all that carbon gets dumped in the soil. You've got microbial biomass there as well. Different microbes have different functions. As they die, then you get this kind of nice buildup. The challenge we have is that this isn't a perfect process. If it was, we'd be in a lot better position than what we are now. Because the challenge we've got is that a lot of microbes in the soil, just like us, breathe in CO2, breathe in oxygen and breathe out CO2 or other carbon-based compounds, including nitrous oxide, which is only a smaller percentage of microbes that pull that out, but there is some nitrous oxide emissions, and other greenhouse gases like methane and others. So the key message here is that because that conversion isn't completely 100% efficient, that's why we're not building carbon at the rate that we're building biomass in our systems. So let's talk about what the most limiting factor is in our systems and what that might mean in terms of the our ability to build that organic matter and organic carbon. So it's really focused on the leaky bucket, or in official term, a guy called Liebig phrased it as the law of the minimum. So basically, you can only fill a bucket or a wine barrel. I live in Rutherglen wine region, have a kind of affinity to wine barrels. But you can only fill that wine barrel up to the point that the lowest hole is in it. When the water starts falling out, then you cannot physically put more water in that barrel. So it's the same approach with anything, and really talks about that's whatever the most limiting factor is for that accumulation is where we're going to end up with. Once we've plugged that hole, then we can move up to the next one. So we talk about soils functioning up to the most limiting factor in that system. And we know there's a strong connection between plant productivity and plant growth and soil carbon. And they're limited basically by the same things. So we know that rainfall and soil moisture have a big part to play, which is a pretty obvious connection. We know that soil constraints to root growth and biomass production also have a really big role to play. And so these are things like sodicity, salinity, boron, potentially even aluminium-13 toxicity, which is another story, compaction, water repellency, crusting, basically anything that is impeding water movement into the soil and is impeding the ability of those plant roots to explore into that soil, is going to have an impact on the ability to grow plants and further on the ability to build carbon. So another constraint that hasn't tended to be a big deal in the Wimmera and Mallee is soil pH. And this is something that acid soils are predominant in a lot of parts of Australia. What we're also finding though is that acidity and acid soils have been detected at least into the southern Wimmera, even on some of those heavier soils and particularly on some of the lighter ones. So as much as acidity and soil pH may not have been something that was high on the red flag status in terms of your soils, we know that soils are acidifying and we're getting acid soils in areas that we never thought we would. So just to cover bases and even just to be reassured where you're at, if your soils may be, you think they're probably 6 or below, just do some sampling, have a look, and then you've got some good baselines that you can work with in future. When you're doing any sampling for soil pH, make sure you benchmark down to 30 centimetres, because that's where we're seeing this increasing in acidity is actually in that 5 to 15 to 20 zone. So bit of digression, but basically soil pH is a really key driver and a limiter into our ability to build carbon. And then soil type, sandy soils can hold a lot less carbon than clay soils, and hopefully Amanda will expand on that further as well as we go through. And then finally, soil fertility and nutrition. So if you don't have the nutrients for the plants, then you don't have the nutrients for the carbon, which we'll go through a bit more. So the key thing is before, if you're thinking that soil organic matter and soil carbon is something that is important to you and you'd like to increase, then before starting down the process of focusing on that carbon or building organic matter, have a focus on your key system as a start to see a broad brush across your system on your soil. Make sure you understand what your system can deal with and what are the big ticket items that you need to get started on. So the key thing is that you need to address those key limitations. If you can't address them because there's something that you can't change, like a lot of our soil constraints, then manage your expectations around organic matter to that threshold. And if you can address them, then work on whatever is your most limiting factor first. Obviously knowing that rainfall per se is something that we can't influence, but how we catch that rainfall and ensure that we get that movement of moisture into the soil is something that we can. So this brings us down to back onto the soil fertility question, and what does it have to do with soil organic carbon? And this is coming back to Rob's note around the connection between soil organic matter and soil carbon, because they tend to be two words that are used interchangeably, and even a lot of the soil testing, some labs will report on soil organic matter and others will report on soil organic carbon. And there seems to be this assumption that they're the same thing. When we look at it in the broader sense, soil organic matter encompasses all the organic materials found in soil, regardless of their origin or state of decomposition. When we filter that down to the organic matter that can't be easily discernible as to where it came from, when you get to the point that you have what looks like a, you can look at soil and say that soil has a lot of organic matter in it, the more ubiquitous kind of breakdown products. When we get to that point, we know that soil organic matter has a consistent ratio of nutrients. So it doesn't, around the world, doesn't matter if you're in the northern hemisphere or the southern hemisphere, there's particular nutrients that are present within organic matter. And this is really key when we start to talk about fertility. So generally, we know that organic matter as a whole has a carbon to nitrogen ratio of about 10 to 1, carbon to sulfur about 54 to 1, bit of subject there according to the soil types and systems, and pretty steady ratio of carbon to phosphorus as well. This is actually the organic phosphorus class, which is less with less flux according to nutrient input. So we know that organic matter is comprised of all this other stuff in addition to carbon. What we also know is because a lot of this material is present within relatively constant ratios, and that there is this constant relationship between organic matter and organic carbon. So years ago, it was worked out as probably a bit of a rule of thumb that if we measure organic carbon and then multiply that by 1.72, then we get an approximate of soil organic matter. So in your lab tests, that when it comes back, if it's reporting on soil organic matter, then that is actually a calculation that's done. As none of the NATO accredited labs and ASPAC accredited labs in Australia will actually measure organic matter. We always measure carbon. So the reason why we measure carbon rather than measuring our whole organic matter is that it actually comes down to what we can physically quantify and literally measure using the instrumentation that we have. So we know that carbon is a constant in soil, in organic matter, and so by measuring carbon, then that reduces the interference and any fluffiness around what else is there. So we have a number, we're measuring an element, and then we can measure the change in that element over time and space using standard methods and standard instrumentation. Amanda, is there anything more you'd like to bring in at this point around the organic matter, organic carbon relationship? I've presented it quite broadly. If there's some more detail, that would be great.
No, I think that's good. The organic matter, we don't often see that in the test in South Australia, but I've heard it a lot from Victoria, New South Wales. So that's an interesting one. We just report in organic carbon. So we've had that discussion about people confusing which one is which one is which. So that was a good clarification.
Perhaps if I could just add something there, Cassie. One of the things that we've seen in the literature in probably, well, in the 210s to 220s was the appearance of charcoal in that soil test, and that's finely divided charcoal, and often in grasslands where there's been burning, which is a lot of the Wimmera, for example, a lot of the grasslands in southern Victoria as well, historic grasslands I'm talking about, there is a remnant of those burned grasses as charcoal, and that comes up in the soil organic carbon test. And so in some situations, that soil carbon measurement can overestimate the amount of humus, the amount of what we call labile carbon that's able to be turned through cycles. And so there's been quite a bit of work about trying to fractionate that organic material, organic carbon, into charcoal and those what we call the labile or the transformed products. It's been done in the labs, but it hasn't been all as successful when it's transferred into commercial laboratories. But it is something that's the ongoing area of science, just differentiating between what's labile or metabolizable carbon, if you like, and fixed carbon. So, and it is something that we need to be aware of. Particularly, I think it's come up particularly here in the Wimmera, where they were grasslands that have been historically burned over thousands of years as indigenous management strategies and it probably also applies in the mid regions of Tassie, the Midlands there. So yeah, just a point about that labile carbon versus charcoal.
That's a really good point, Rob. Which it also pulls into the definition of soil organic carbon rather than soil carbon. Which is something that's actually relevant into parts of the Mallee, is when you've got the presence of limestone or other carbonate substances in soil, which are naturally occurring. So some of our highly alkaline soils and into South Australia as well are likely to have presence of calcium carbonate or other carbonates in soil. So this is the key thing. So we can measure total carbon in soil, which includes those carbonates and other materials. And then we can also measure total organic carbon, which is the carbon derived from plant material not these naturally occurring substances. So with the charcoal, then that's a really good point. So I guess where we look at from there is potentially if the carbon values are unusually high, don't seem to make sense as far as the agricultural management of that system. And there's a chance of having charcoals in there. Some of that may be visible, but yeah, Amanda.
Sorry, I was going to butt in there. We often find, so it's depending on what test the labs are doing is how much they will pick it up. So the often test they use is organic carbon Walkley Black. That's known not to pick up so much charcoal or the calcium carbonate in there. But as you said, that total carbon test picks up both the charcoal and the calcium carbonate. So you have to be a bit aware of which test you have. And we still advise most of our farmers who have calcareous soils to definitely have the organic carbon Walkley Black. If you're talking about looking at it from a carbon market or a project perspective, they need to have the total carbon. And then there are various methods to remove that carbonate portion, so that limestone out of your soil. So there are more and more tests that are being available for growers for farmers to use. So it's about being aware of which test you're using and for what reason you're testing it for.
And Amanda, will most labs use that same terminology for growers out who are if they're looking to ensure that they get the right test?
They are. So they are. Everybody's trying to use total carbon, and that's a test that encompasses all the fractions that Rob was talking about, the active and the recalcitrant, the charcoal. And organic carbon Walkley Black is, or you'll see WB, is probably the most common test that's used across Australia.
Yeah. And I'd hope that most of the labs pre-treat to remove calcium carbonate, which carbonate is being carbon also. And some of our soils in the low rainfall zones here have got quite high levels of carbonate, and that can falsely come up as carbon. But I think the standard procedures in laboratories remove that calcium carbonate before they do the Walkley Black or the Lico carbon. Can I confuse things even more?
Absolutely.
Because when we hear about farmers having carbon, storing carbon in the soil, this term of soil carbon stocks comes up, and equivalent CO2, and this is one of the issues. Cassie, do you want to mention, or Mandy, do you want to mention how carbon stocks differ to carbon percentage in a soil? Because carbon stocks are what is often thought about as building up.
Amanda?
So carbon stocks are very similar to nitrogen stocks. It's when we're talking about incorporating the mass of the soil, so the density of your soil as well. So we end up talking about tons of carbon per hectare of soil down to a certain depth. So you're really just considering your weight of your soil. And that's really important when you have different masses or weight of your soil, and then you can compare a consistent area. So if you're looking at a sand and a clay, you're looking at a similar soil mass to compare your carbons across, a similar way to what you do with your nitrogen, looking at there. And carbon dioxide equivalents are another thing. Again, it's trying to put carbon on a standard greenhouse gas emission. So everything is talked about as a carbon dioxide equivalent. So if you want to know how much your carbon dioxide equivalent is with your carbon stock, you multiply that by 3.67 and you'll have a carbon dioxide equivalent.
So just to give an example, if you've got 1% organic carbon in the soil, if the soil's got a bulk density of about 1.3, that means you've got 13 tonnes of carbon in, say, the top 10 centimetres, which is your sampling depth. Now, if you convert that to what is traded in the carbon markets in terms of global warming percentage, that 1% carbon is a 48 tonnes of tradable carbon CO2. So, that's where we sometimes get confused about carbon percentage, carbon content, and carbon trading. And then you need to have those terms pretty well defined. And the testing procedures, I think, Cassie, you're going to mention in a minute, are fundamental to that. If you understand the bulk density of the soil, which is how many kilograms per tons per cubic metre, I think that's where probably one of the biggest issues is, and the depth to which you're going to talk about. And I think it's 30 centimetres is the standard depth for carbon trading. And so anyway, that's enough from me for the moment.
No, that's all right. Rob, we'll come back to the carbon trading stuff later. If there's also some recent publications out there, Tom, that we can circulate to help in this space as well, and kind of context what that all looks like, and kind of what's involved with some of those methodologies under the carbon trading. But a key thing with that, I guess, at the moment is that the value of us. So this, and with the carbon trading, then, and just to context it, you can only trade additional carbon. So if you know that you have 32 tonne of carbon in your soil, that's not a figure that you can then put a dollar on and potentially trade it. It's actually the additional carbon above that which you build under a new practice. So there's all these requirements around demonstrating that you're changing something. So you do your baseline sampling, and then you change something, and then it's additional carbon on that which is actually traded, which dramatically decreases the total stocks potential in that. So we're talking, if you can increase your soil carbon by 0.2 or 0.3%, which would be a really good effort in the Wimmera and Mallee. 0.5 would be kind of buy the man a beer, this is amazing. Get to that point, and that's the difference that could be traded. And when you put dollar values on that, the dollar values don't stack up at the moment. The risk is really high and the returns are really low, and it's a long-term commitment as well. So a lot of stuff with that we can talk about more later, but just to context that the real value of organic matter and carbon in our farming systems in the Wimmera and Mallee is around the system benefits, and it's around how that carbon through organic matter can support all the benefits and activities and functions that can lift your productivity system, which then has so much more value to you as a farmer than the equivalent of 0.2% or 0.3% increase in carbon with a trade, and then go from there. So when you look at all the different functions that organic matter adds to in soil and contributes to, if we were to put a dollar value on every one of those and the longer term sustainability benefit of that, then I think that's really where, at the moment, the real benefits of focusing on soil carbon and organic matter are in these systems.
Yeah, and at the moment, the ECO2 price is about $20 a tonne. So that translates to about $4.50 per tonne of carbon in your soil that you would have to add to have a tradable amount. You'll explain that later, I know, but that's just a very important point, that it's actually, that carbon trading part is somewhat irrelevant in an oversight view when compared to what you can do with your farming system by managing soil carbon, soil organic matter.
And before we move on, Cass, and you might come back to it later, but you touched on that idea that in order to access it, even in the very first instance, you have to do some sort of change to your farming soil carbon. So for our group in Mallee, who are doing what we consider to be best practice farming, that change is a very difficult thing to.
That's a really good point, Tom. Yeah, that's the frustrating thing around this whole emission reduction fund and carbon trading, farming, all this stuff that the government's working on now, is all the really good farmers who have been innovating and doing, really been on the edge of new thinking and embracing what's learnt through science and adapting it to their systems. They're not eligible to get any reward from this because they've already increased their systems to the point. They've made all the easy wins, and any incremental increases from here are kind of blood out of a stone. You're really looking at that diminishing return angle. So which is completely disappointing with the whole thing. But yeah, the key there is that you're by recognizing the value that you've been doing for the last 20 years in your system, and how much better your system is and how much more resilient that system is such a better way to go. And one last point with Robin, we'll come back to it later, but what was the dollar value you mentioned? It was about $4. You're on mute, Rob.
First one to do it, Rob.
Yeah, well, welcome. Yeah, $4, about $4.50. It's about $20 a tonne for ECO2 on the current Australian market. It's
Yeah.
doubled in the past couple of years. So
Yeah.
And there are predictions it's going to go up to around about 50, isn't there?
Yeah.
When you
Yeah.
look at the projections, but it's a long way off.
But then if you look at that value, there's all these fine print discounting that happens through that. So you have to discount your background emissions for the last 20 years off that land. You have to discount your emissions within the period of time that you're measuring that change. Then you discount again because you're measuring a soil carbon and there's increased variability. You discount again if you only want to sign up to a 25-year contract, not a 100-year contract. And then the broker gets 25%. So you probably get a beer out of it and that's about it. So anyway, we digress. But yeah, just to put in context, organic matter within the farming system is such a better investment and such a better way of looking at things than trying to make a quick buck on a carbon trade, particularly in a lower rainfall zone where our capacity to build is completely threshold limited by our rainfall. So speaking of the value in the system, let's come back to the whole soil fertility aspect because, as we've said, this is a really big deal in terms of organic matter. So we know that if our organic matter is comprised of these discrete ratios, very much biologically driven and dictated ratios around carbon, nitrogen, phosphorus, sulfur, and everything else, right? So to hold a certain amount of organic matter in our system, we need to hold the nutrition or the nutrients within that matter as well. If you deplete your soil fertility, so you're mining that organic matter you're completely mining that to grow a crop and you're not replacing it in some form, then you're actually reducing your total potential to hold organic matter. So if you take out, so we know carbon to nitrogen, very, very strong ratio. This is one of the most locked in, biologically governed ratios in organic matter. So it's really easy to talk about. Carbon to nitrogen ratio of organic matter is 10 to 1. So if you take out 1 unit of nitrogen through mineralisation, which happens all the time, so it's not like we can stop it happening, right? But if you take out that nitrogen and you don't feed it back into the system through your bigger picture strategy, you lose 10 units of carbon in that process. So when we mineralise nitrogen, when we convert it from organic nitrogen structures, such as those that come from plants, and we convert that through mineralisation to ammonium and nitrate for the plant, then we lose 10 units of carbon and CO2 through that process, basically. Which means that if your nutrition program around your cropping and your farming systems, not just cropping but pastures as well, if it's focused around just putting enough on to satisfy that crop requirements, then we're really not, we're kind of incrementally draining our bigger bucket in terms of organic matter. And this is, as I mentioned, through this process called mineralisation, where nutrients in organic matter get converted to plant available. So yeah, it's conversion of complex carbon bonded structures, such as coming from the proteins and the carbohydrates and a lot of the bigger complex structures in plants, and as they're broken down through microbes and broken down eventually to our plant available forms, then an example is the conversion of our protein to ammonium to nitrate, then we get that net loss of carbon through that system. So this is a really big deal, and it's something that's not really considered in a lot of the thinking around building carbon. It's completely a system approach with that. So just on the nutrients, it's just worth if we just pause this for a second, and I just want to flag just some concepts to put our thinking in the right space. So when we think about our undisturbed native systems, So our forests and our native environments that haven't been used for food production, these are all sustainable cycles where the plant material is recycled at the point of growth, right? So you grow your tree, litter falls, gets broken down on the spot. That material is then recycled and becomes available to continue to support plant growth at that site. The challenge we have in ag is that all our agricultural activities rely on product removal or export. So it doesn't matter what we're growing or what we're feeding or what we're doing. If we're, any grains, even our pastures, we're exporting meat and wool, hay, everything that we do, we grow something to export for food. So because of this, we're taking nutrients and alkali, so a net high pH, so our cations, we're taking them off-site and somewhere else, which actually creates a bit of an oxymoron kind of thing to say that if we want to run a sustainable agricultural system and continue to feed the world, we actually require those exported products to be replaced. So if we don't replace what we're taking out, we're exploiting that system and effectively mining it. So this is just something to consider. There's a lot of discussion at the moment around holistic farming and around using natural cycles to support our farming. And just to put it out there that whilst we always want to maintain and enhance our biological systems as much as we can, they're still supporting farming, which means that every nutrient that you take off needs to be replaced. And the only nutrient that the microbes can create in soil is nitrogen through free-living end fixes and through our awesome rhizobium supported pulses and legumes in our system. They're basically, the role of those plants in maintaining nitrogen and maintaining organic matter in their systems cannot be emphasized enough. They're the only real way to get significant amounts of nitrogen from the atmosphere into our soil. Every other nutrient that the plants take up and then is exported, phosphorus, sulfur, potassium, calcium, magnesium, everything else that we put into our plants, that our plants take up and our product is removed, cannot be created in our soils. So our soils have a finite bank of those nutrients based on the mineralogy. So by increasing the microbial cycling in our systems, we can increase the rate and the efficiency with which those microbes can access pools of those nutrients in soil, so increase phosphatase activity and VAM, fungi, etc., to scavenge and source that phosphorus. But that phosphorus is still a finite bank. So if we're not putting stuff back in, then we're going to reach a point where we've run out. And our soils are, as we know, some of the worst in the world in terms of nutrition and fertility. We don't have the amazing soils of the plains of America and parts of Europe, which are amazingly fertile. Ours are already kind of a few million years behind the 8 ball. So we're not talking these massive banks. So just to put in context, whenever you're reading something or talking to someone and they're saying that they're tapping into the microbial system to access nutrients, then it's still a finite resource that they're accessing. So sorry if I bang the point a bit, but just really important to put that nutrition in context, that it's not something that we can just keep dragging out.
I think, Cassie, it is an important point, because the sustainable system is one where inputs and outputs are balanced. And as you said, the only thing you get, well, you don't really get it for nothing. The only thing you get inputted is nitrogen. It does cost you energy, and it does cost the system energy, and it does cost the system some nutrients. But if you grow a 3-ton wheat crop, 60 kilograms of nitrogen and 10 kilograms of phosphorus go out the gate. Now the stubble is kept there and not burned now. So that some of the nitrogen and a little bit of the phosphorus, the small amount of phosphorus in that does stay there. But if you cut that straw and sell that to a mushroom grower, that also goes. So, and that's a few more kilograms of and probably another 0.5 to 1 kilogram of phosphorus going out the gate. So, you know, you can't emphasize enough that a sustainable system in our situation where we've got productive, highly productive, well-managed systems, stuff goes out the gate. So you've got to replace it from through the other gate.
And another thing, if I could just add too, is that we were talking about the fractions and about the importance of having those fractions in carbon. So we have that fresh, the residues there, the particulate fraction, and we want to transfer that. If we want to have carbon long-term storage, we need to transfer that to the humus fraction. And this requires nutrients that you showed before. So if we don't have the nutrients in the soil, we can't enable that transformation to occur. So we're going to have our carbon in a state that's always readily available for microbial decomposition. And so what we need, if we don't have enough nutrients in our soils, we can't often transform that into that long-term storage. And the long-term, the humus part is what we are aiming for to get the most benefits for our soils.
And so, Amanda, that would connect in with the reasons why in a lot of our systems, our cereal stubbles aren't efficiently breaking down. So as much as we say there's all these tons of carbon in our stubble,
Mm-hmm.
and we're retaining all our stubbles, but why aren't we increasing our soil carbon? What have I done wrong? It's a lot of it is about that imbalance in that nutrient availability, isn't it? Because in our pulse system, if we grow a pulse after a cereal stubble, then all that stubble gets completely broken down and disappear. So it's really that inefficiency. Yeah.
We did a study in the southeast there. We were looking at where we had sandy soils and we had clay additions, so clay spreading or delving in there. And the limiting factor for where we didn't have transformation to carbon came first on the rainfall. If you were below 350, you didn't have quite enough rainfall. But then the next thing was nutrition. So those sites that had high nutrition had much higher carbon stocks, didn't have enough nutrition in the soil. We didn't have carbon. So it's a really important factor that is often overlooked.
Just to add one more comment there, the amount with a stubble retained system, the amount you put in is not very much on an annual basis. So 3-ton crop's about a 6-ton stubble, and a 6-ton stubble is maybe on a dry weight basis 40, 50, 60% carbon. So that's about 3.5 ton to 4 ton of carbon in that stubble, which then can recycle. And that's not a lot less than that. The amount that's recycled is pretty low. And some of it is also lost as it's respired. The bugs, as you said at the start, Cassandra, do breathe in oxygen and breathe out carbon dioxide as they metabolise stuff. And some of the carbon that they use, some of the carbon is ended up being part of the metabolites. So.
Yeah, and there's figures of up to 70 to 90% of the carbon inputs we put in are mineralised. So they're not lost from the system because we need to have that carbon in there to get the microbes going. A prime factor of having carbon in our soils is to feed the microbes so that we can have mineralisation. It's considered a loss when we're thinking about carbon markets, I think, too, sometimes in that way. So it's about how do we refine that figure from a 90% decomposition down to a 70 if possible.
Yeah. The other thing, though, which I just realised we hadn't touched on, and actually I can't remember if I talk about it later or not, but we actually don't give credit for what we are doing right. Because when you think, because I talk to a lot of farmers who say, I'm maintaining all my stubbles, I'm doing everything right, but my carbon values aren't going up, right? But their carbon values aren't going down, which is actually a really important point. So because we know that we can't hold organic matter, we can't hold carbon if we're mining our systems. But because we're getting that continual flow of nutrients from organic matter to mineralize it through mineralisation to plant available forms, the fact that that's happening all the time, the fact that all the carbon that we're losing through that process isn't resulting in a decline in carbon, it means that they are actually getting a significant portion back in. So if they're pulling off 3+ ton wheat crops and 1.5 ton canola, 2 ton canola, whatever through the system, and they're not losing carbon, then that's something that we should actually be recognising and rewarding. If you can maintain carbons above 1.2 in a Wimmera and Mallee system, and maintaining it sustainably in a profitable, productive system, then that's actually worthy of, awesomeness.
I recall this presentation that I heard around the stubble initiative, which was a GRDC program maybe 5 or 7 years ago. And one of the farmers, one of the comments from that was, we've retained stubble, we've direct drilled, we for 10 years, and we haven't changed, we haven't increased soil carbon. So why are we doing it? And the point was that, well, you're not getting soil blown away for a start, which also loses a soil fraction. You're protecting the soil surface, you're improving water infiltration, etc. So the benefits of retaining stubble are far beyond the carbon benefits themselves, but that's also an important aspect of it by keeping that labile carbon cycling and cycling nutrients with it as well.
So if you're, and I bet that farmer's productivity has probably gone up over that time.
Yep. Yep.
And if they're maintaining their carbons in that system, then that actually recognises good practice.
And the stubble initiative as well, Rob, was done on the back of the drought, we remember. So the farmers were just getting through with minimal, managing their productivity for profit. So the understanding is that if we haven't got those inputs going in at the rate that they need to, feed the crop, but to feed the system, Cassie, to steal your line, then we won't see that increase in soil because of that lack of nutrition.
And just, sorry, Rob.
I was going to say, Cassie, you mentioned 1 to 1.2% as being a figure that would be good. That figure really changes a lot as you go from place to place. Like if you're in the Mallee, 1% would be a luxury. If you're in the Western District, Victoria, or some of the lower southeast of South Australia, you might be 2.5% might be okay. If you're in the Currumbara peat soils where they grow asparagus, you might be on 5% organic carbon. The reason those numbers are there is because, as you said, the rainfall and the environment dictates what the soil carbon top level is. And you can sample outside your fence and inside into your paddock, and you can get an idea of some of the difference there. And we did some of that again a few years ago. Everything I've done has been a few years ago, by the way. And there are significant differences between those in and outside the fence, because the outside the fence is really that natural system that you've been managing, not been managing, but things have just been cycling. And I think thinking in the Mallee that it would be fantastic to get to 2% organic carbon is tell them they're dreaming, so to speak, because it's just not possible unless you buy 200 tonne of brown coal and bring it up and drop it on your paddock.
Pretty much. So that's exactly right, Rob. So I was using the 1 to 1.2 as kind of a gold star effort in the probably that's still probably more the Wimmera. Although on the clays you've got more potential, but but it really is about managing the expectation of what a really good carbon value is. Obviously on the sands, your capacity is so much less, and we could probably work through that a bit more detail in the next presentation, where we can pull through a lot of work, Amanda, that you've been involved in, and others around that whole sand carbon, and how we can work with that. Yeah, so they're definitely dreaming, and it's just really about if you have some good measurement in place, and you understand your system, and you can see what constraints you're dealing with and what options you've got to tweak, then you can certainly build on that. But yeah, a 3 and 4% carbon values in the Mallee is, yeah, you may as well just bring in coal, which will do, yeah, which won't give you a lot of the benefit that you're looking for. Okay, so just finally, just want to flag a few weeks ago, I had the pleasure of listening to James Hunt give a presentation to one of the other GAPP groups, and he flagged some research that had been done to demonstrate that as over time as soil nitrogen levels increased in a replicated experiment looking at longer term systems, then soil carbon values also increased. So where you build up that system fertility, that really gives you the chance to build that up as well. But completely understand that profitable farming systems, there's always a balance sheet going on, and the dollar signs tend to be of high value. Well, they have to be of high value. So, as much as we say just add on as much nutrition as you can, it has to be obviously economically practicable, and focus your efforts on where you'll get that largest, where you can knock off that next constraint.
Okay. I also add something, sorry to come in again on that, but that point about, nitrogen pools and building nitrogen. We had a long-term experiment that ran for 19 years with Insitec Pivot, just 10k out of Horsham, looking at N and P rates. And over the journey, if you only had nitrogen on the system, the soil organic carbon didn't go up at all. But if you had nitrogen and phosphorus, the soil organic carbon went up a little bit, but it was a significant increase in soil organic carbon over that journey, over the period. So it took a long time, but we certainly saw that you had to, as your point exactly at the start was, you had to have all the nutrients there. Now this was probably a reasonable level of sulfur, and we also had zinc going in the system, but N and P together were the things that really helped manage that soil carbon, which is a subtext of getting profitable farming systems. And it was really, that was an added benefit to us over that period. It wasn't very much, it was like 0.2%, something like 0.8 to 1%.
Well, that's huge. That's awesome. Yeah. Actually, with that, Rob, just so in addition to everything else I do, I also work with individual farmers through the Wimmera and Mallee, and just provide additional support with them, with their agronomists. And something that I've been picking up is that I really start to worry that there's some subclinical P deficiency happening in those systems, where the P levels are so on the line. And knowing that as you completely know, that most of those recommendations around P levels were done in incorporated mixed systems, not our stratified no-till systems, which means that the plant probably isn't seeing a lot of what the soil test is saying is there, because of there's accumulation of phosphorus on that soil surface due to the plant litter deposition. So I really think that phosphorus is probably, as you say, like one of the key limiters in that system, that just nudging that up a bit could actually create a lot more benefit.
Yeah, I think, again, over the journey, growers went through a period, the millennium drought, and they did pull back on phosphorus inputs. And subsequent to a few good years, they haven't really pulled it back up again. And that phosphorus pool is declining, which has impacts on the production system and just general plant growth. It also impacts probably more the legumes in the system than the cereals or the canola. Canola is pretty efficient at getting low phosphorus pools, and so is chickpeas. But the impact of low phosphorus on legumes means you don't get the input of nitrogen into your organic nitrogen pools, organic matter pools. So it's sort of a double kickback. If you have low phosphorus, you've got low legume growth, low nitrogen. So you end up kicking on to a low N and P system when you get into the cereals.
Yeah. Now, Tommy, probably I don't know how we're going for time, but we'll keep kicking on. Give some time for discussion at the end. So just as we mentioned, we need to start thinking about our system fertility. And as we increase our nutrient levels, increase the efficiency of that conversion of our stubbles to soil organic carbon, which then we get more kick-off in terms of microbial activity. And just flagging as well, microbes can't function without nutrients. So they need to get that nutrition well.
Before we go on, Cass, there is a question from the audience that's around microbes and just understanding what the health and makeup of our microbe population is in the soil. Now, is there data around that, and how can we measure it as a...
So that's probably a whole new conversation around the actual microbes and their makeup in soil. What we also know that a lot of the testing we can do with microbes, so some of the DNA testing, etc., can say what bacteria and fungi you've got, and then there's different tests to look at functionality and genes and stuff, and then you've got your basic microbial biomass and others. But the key thing to think about is that the microbes are like the people in the system. They respond to the environment that they're around them. Probably people is not a good idea because we'll just go and chuck in an air conditioner or order in Macca's. But when you think about it, they have to respond and react to their environment. So just like we're saying, and it's all part of the same story, that we can't build organic matter if we have our soil constraints, because our plants are constrained. That means that our inputs are constrained and our organic matter is constrained. But organic matter accumulation is actually constrained, so that the connector in that is that if our system isn't functioning well, then our microbes aren't functioning well. So by basically building the house and making sure that everything's in play, that then facilitates the microbial populations to flourish that will do well in that environment. So if we're under a pH constrained system, so as an example, if our pHs are less than 5, our rhizobium, which are needed, as Rob mentioned, for our pulses to work properly, aren't going to function well. A lot of the other free-living end fixers are going to turn up their toes and go somewhere else. A lot of the nitrogen cycling microbes that are involved in that mineralisation process from organic N to ammonium to nitrate, they don't function well. So we actually kind of break those cycles. So if we increase our pH levels, then we actually enhance all those microbial systems to function well. So that's just one example. Also, as we go into lower pH systems, generally our good bacteria as a general population crack the sads and don't work. And so it becomes very much a fungal dominated environment, which may not always bring in the fungi that you want. So basically, if we set things up so the plant is doing well and the plant isn't stressed, except for water and rain, if we do everything we can to support the plant, that then supports the microbes to function well, which then supports the conversion into organic matter. And as we're saying, plants need good nutrition, the soil needs good nutrition, but the soil needs good nutrition because the microbes need that nutrition. So if they don't get the balanced diet that they need, so adequate levels of NPKs, etc., probably don't go to antsy-pantsy kind of detail about it, but if you're providing enough for the plant in levels that are above the, if everything is in the happy range for the plant, then everything will be in the happy range for the microbes. So yeah, N fixation is really the only thing that microbes don't need if there's enough N. So yeah, the N fixation part of the process is where they can pull in their own nutrition if that's working well.
So Cassie, around that idea, we do add bacteria to soil. So we do add rhizobia, for example. We inoculate plants with rhizobia. There's also been a lot of interest in using mycorrhizal fungi as being a introduction into the soil. Are there any other examples of if we added microbes to the soil where it would do a good job, you know, it would be a great thing to do rather than changing the soil background.
So that's a really interesting point, Rob. There's a lot of interest at the moment around inoculation with endophytic bacteria and fixes into the plant. There's some big companies that are playing in this space. There's potentially a role for it. They have been demonstrated that they may support reduce stress, you know, managing stress responses in plants and have other functions. The challenge we have, and the other thing is so that's within the plant. So that's actually looking to inoculate a plant with these things, which is in probably a more controlled environment than the soil. In the soil, if we're looking to apply a microbial solution to our soil, it's like putting 10 people into a crowded MCG and asking them to change the theme song chant or to be heard above the din. They're really they're not as adapted to those systems, and they're not as efficient in those systems, and they're likely to get outcompeted incredibly quickly.
The analogy I've heard is it's like landing a naked man on Antarctica in summer and expecting them to survive and reproduce in a hostile environment. They're putting microbes into soils, unless there's a habitat for them.
Thank you, Rob. That was an image I probably didn't need this morning. But exactly right. So if you're adding microbes to a soil system, you're basically trying to influence something that is subject to everything else, and the microbes aren't going to compete. The endophytic work, where you're inoculating into a plant, there's enough evidence internationally that there may be a role. The challenge we have is that the plant, it's kind of still, it's like the tweaking around the edges kind of work. The challenge as well is that they won't always show a response. So it might be a one in 6 years that you actually might see a benefit of it. Because you're working with a complex biology, introduced into a complex biology, then the different permutations of that are endless. So we don't have the consistency and confidence in what they do. And obviously every product and every bacteria strain behaves differently. The quality of what you're dealing with from a product, the efficacy of that, the degree to which that inoculating bacteria can function in the systems that you're putting them in. There's so many unknowns. So it may become, it's kind of like a ideal that it'd be awesome if they work. There's not enough Australian-based evidence yet to say that should be one of our key framework. I think there's so many other things that we need to focus on, and the role of pulses in our system for nitrogen is something that is so well known and so efficient that I think that's really where we need to be supporting.
And that goes back to your barrel at the start, doesn't it? Where, unless you've got the other aspects of your system, your nutrient management, your water management, spot on, then that extra little bit of microbial stuff mightn't have any effect because it's still nutrient or water limited or temperature limited. So yeah, I think it'd be nice if these things worked and we keep an open mind on them. And if we understand the processes, then we might be able to find places where they're able to be deployed, some of these very interesting, very novel strategies.
I think it goes back to what you said at the start too. It's about focusing on the soil, what we can do to get our soils to work, to be productive, to function well, create the environment, and then what will come next. I think we will be ready for it to be. So like you said, if you introduce microbes into a soil that's not ready for it, or it can't survive or thrive, it's just considered a waste of time and money. So if we can work on those limitations, get our soils working as well as our productivity system working as well as we can, what will happen next, I think, is what will be there. So that focus on soil health, soil function should be uppermost in our minds, I think.
I think you're right, Amanda. I think it's key to keep, as you say, keep an open mind with this, that there's enough research, some really good, credible stuff coming through to demonstrate that there could be a role for biologicals and other inorganic biostimulants in our systems. The challenge we have is that it's still done at a very high level. Sorry, not a high level, a very very enclosed, very controlled systems, and taking something that was generated and put into a packet in another country and then spraying that onto our paddocks and expecting a response when we don't understand what all the limiters are around even that working properly. So I think it could be the next thing, but I think there are so many easy wins and guaranteed wins that we can do. If we increase our soil fertility, that's a big win. If we can keep everything else going well, and we just watch and learn, and over the next 10 years, I'm hoping that we start to get a little bit more clarity around the role of some of these things.
And we've focused on fertility, but also pathology, soil pathology, disease organisms in soils. We have to keep a mind on them all the time because they can occupy a niche that appears, particularly if we're not in a in a polyculture, but one that has similar plants in the system. So certainly it's not just fertility, but it's pathology, soil biology, pathological organisms in the soil as well.
That's right. Yep. And which comes back to the stress and stuff. So if we support the system so that the soil biology can do well, we also then support diversity within that system as well, because we're not selecting for certain microbes because they only function in that high acidity or poor water crusting environment or whatever. So if we can support our soil system, then we support the diversity of microbes, which then hopefully then support in terms of that pathology as well. Okay, so finally, so just wanted to check that we're almost done. So finally, we talk about measurement and monitoring. So obviously, if you don't have some numbers around soil carbon, then you don't know where you are and you don't know what kind of your potential is. And so just flagging that within a paddock, there's massive variance in terms of soil carbon. So this is just taken from some work that we did last year, where we actually overlaid the carbon farming initiative and the ERF methodologies for carbon trading onto some carbon sampling, just for kicks, to see what it actually looked like in terms of carbon stocks and dollars and everything else. And Tom, I can send that report through that this came from, if you'd like. But so just to demonstrate that over a paddock where we used all the appropriate methods as if we were carbon trading, we found really strong variances in our soil carbons across that paddock. And this is a paddock that looked uniform. It was dead flat, riverine plains kind of environment. It you'd think it was, about one. You'd go, yeah, it's all about the same. So you can see that in some parts of the paddock we go from 0.5 and then we go all the way to 1.6 in areas that don't look any different from the surface. So if we take the classic approach to soil sampling, which I was taught when I went to uni a few years ago, that if we transact through there, we cover all those different areas, we chuck them all in a bucket, mix it up, we take a sample, send that to the lab, then that's our number, right? What we're getting is that average across there with all the variance that's built in with that. So that means if we come back in 5 years' time and run that same transact again and say, let's measure if we've got a change in carbon, we're not going to measure any difference because we keep bringing in all this variance across the line, which may also be part of the reason why farmers are saying that I've been doing everything right, but my carbons haven't changed, which means, okay, so what's your measurement? How are you sampling for that? So you're basically setting yourself up to fail as far as carbon sampling and carbon measurement over time if you're running transects through. If this was a zone of similar soil type and you had done all your EM and you'd assigned paddock zones and you were measuring within a defined zone, then you'd have a much better chance of capturing that carbon change because you know that you're within the same soil type and the same aspect and the same elevation and everything else. But ideally, the GPS located sampling is probably the most sensitive approach in terms of measuring that time series change. So the idea is that then if you were to measure 2 parts in your paddock, you'd see you had a 0.9 here and you go, not great. Then you find you've got a 1.6 here and you go, okay, well, that's really cool. What can we understand more about the differences in this part? Is that where the hay always used to get rolled out? Is that where something happened? Or is there something that, is there? Or is it a different soil type? So at least if we're measuring from a point in space, then we can assign a change over time with that. And if we wanted to use that sampling as a way to look at our system to understand our constraints and what that means, then doing some depth incremented sampling of 0 to 10, 10, 20, 20, 30, down to 30 or 60 centimetres basically gives us a really nice snapshot of our whole system. So what's potentially impeding root growth, water movement, plant growth, and then carbon with that. Of course, measuring carbon down to 60 centimetres would be a waste of money because we don't find much at depth. So even if just the topsoil with carbon, and then look at your other factors as you go down. So finally, plant productivity, carbon is completely connected. We know that each soil is threshold limited with our Mallee versus Wimmera sands clays, which we'll delve into more next time. We focus on system fertility rather than crop nutrition. Soil organic matter is a dynamic entity, as we've talked through, so even maintaining levels. And I've put 0.8 there as kind of a threshold. As we know, below 0.8, we have very limited microbial contribution. So even 0.8 in a sand would be amazing. And accurate sampling over time to track that change and consider that kind of your triannual soil health check. And that's all I have to officially say. Sorry we took so long, Tom, but I'll stop sharing now. And these slides can be available for the group as well if they wanted to go through some of that detail.
No problems at all. Thanks, Cassie. I think that was really informative and a great place to start from. Has anyone got any further thoughts from the audience we have live today? Any questions coming from you guys who are listening in live? We can go around the room for starters, Rob, and see just if you've got any takeaways from today that farmers to start thinking about the next little bit.
They're all having a cup of tea, are they?
I think so.
So also, Tom, if if you've got any thoughts you'd like to kind of talk about further, or things that you think we've missed, or something you really want to go through, or farming systems that you'd like to kind of talk through next time, then please let Tom know. We're more than happy to even work through some specific scenarios if that's of value.
There was a comment came in before, Cassie, around that the idea of acidity increasing in continuous cropping systems. Is there anything the farmers are doing to try and mitigate that issue, or is it well understood the reasons why that acidity is increasing in some soils? Yeah.
So that's quite well known, Tom. The kicker we've got is that we're growing really good productive crops. And so every time we take off that crop, we take off high pH material. So all the things that make our grain really nutritious, so the high in calcium, magnesium, potassium, all these things that are real, and phosphorus and nitrogen, all those things. But particularly our cations, when we take them off, we also take off what you call a net high pH, net alkali. So everything we take off farm, it's not just taking off nutrients, it's also taking off that alkali, which means that agricultural systems by default are actually acidifying. which is a complete bugger. You know, we do really well and we pay the price for it. So then, yeah, as we grow bigger crops, we take off more alkali. Also, because we've got more nitrogen cycling in our systems, that nitrogen is also contributing a component of that acidity. But I would say that the key thing to think about is that alkali removal. And so hay is actually one of the worst things in terms of alkali export. But even, you know, a pretty comfortable cereal or canola crop also pull off a lot as well. So we've got that, yeah, we've got that happening, and the challenge with is because of our continuous cropping systems have a greater net export generally than our pasture systems, that things are happening quicker. And acidity will happen quicker in our sandier soils, with our clay soils having a greater capacity to buffer against that. But even our clays, so I sampled a heavy clay in near Jerilderie, that was, you know, always kind of, they've never sampled for pH for 20 years because it was so high. That had been under continuous rice production for 20 years. It was down to pH of 4.3, down to 20 centimetres. So even the soils that we thought were kind of too good or so good that they weren't acidifying are actually starting to give us pain. So the key thing is to measure your pH levels down to 20 or 30 centimetres, just so that you know what you've got. Don't just assume that you're all sweet.
We've got
Cassie,
a couple of questions. Sorry, Amanda, go for it.
Sorry, Cassie, do you do yours in different depth increments when you do it, or do you just do a 0 to 20 centimetre sample down?
So definitely increment, Amanda. Yeah, so if we have a system that has been through some disturbance, we're comfortable doing the 0 to 10, 10 to 20. If you're in a no-till system where you haven't had any disturbance for a very long time, then do 0 to 5 and 5 to 10. And that will, because we'll get that alkali deposition back onto the surface, some of it through plant litter, and that's not moving to depth.
We are seeing very, very similar patterns happening in South Australia. Our safe areas, which are very fastly acidifying too. So it's a national problem.
It is, yeah. And if you're applying lime, you have to incorporate it.
Mm-hmm.
You can't just broadcast it because it will just sit there and not do anything. So that's a whole new story. But yeah, massive interest in investment happening around acidity and lime.
And acidification can also occur on alkaline soils, of course, which isn't such a bad deal. And that long-term experiment I mentioned before, where there was a lot of nitrogen added and we got nitrate leaching, we dropped soil pH by half a unit from about 7.3 to 6.8.
Right.
Over those periods. So, I mean, that was a huge amount of over-application of nitrogen, but certainly nitrate leaching in, as well as the removal of cations, can occur on our alkaline soils. So don't just think it's a pH 5 or 6 issue. It's a universal issue. It's a function of our farming system that because we remove stuff, we have to you get nothing for nothing. So you remove things, you've got to think about how your strategy to replace them.
And unfortunately, lime is really the only good way to do that at the moment. So I've been encouraging different research organisations to consider what our options are for future, because lime's a finite resource. But at the moment, yeah, you need to apply lime. And of course, when you apply lime, being calcium carbonate, then and with some magnesium in that there as well, you're also then replacing the cations that you've been taking out.
You're also
over that time.
Carbon dioxide. So
yes.
There's a global warming footprint of liming. Sorry to tell you.
Yes, I know. But yeah, in the big picture, it's yeah, I reckon anyone would be happy to take that hit in order to keep growing something.
Absolutely.
Yeah.
So the questions from the audience, Cassie, we have is, firstly, is vetch the best way to increase organic carbon in medium low rainfall areas? And is there any research to compare vetch chem that's been chemically fallowed versus cut for hay or grazed, and in terms of organic carbon?
So I haven't had a lot to do with vetch particularly. I'm sure Rob and Amanda would have a lot more to say about this, but certainly I would say any legume that grows well and has a place in your productive farming system is a really good place to start. And if you can keep it in the system, obviously that's the best benefit rather than taking it all off for hay.
So hay is still exporting something from your system. And if you take it out the gate, it's exporting nutrients, and therefore.
Yeah, but you should still be getting some benefit from that end fixation as well. But I haven't been part of any work particularly in that space. Amanda and Rob?
Yeah, we did, again, in the olden days, we did some of this work, and BCG on their records have got some similar things. In a 1 year situation, really, if you compare chemical fallow and grazed or hay removes the most, grazing removes a little bit, and chemical fallow preserves quite a lot, but it's usually done earlier in the season when there isn't as much growth as compared to a hay crop. So in terms of organic carbon, it's a minor increase, but what you've done is you've actually preserved some nitrogen in that strategy. And in the Wimmera and Mallee, in the Mallee in particular, the biggest benefit is actually weed control with those green manuring situations. We've found, that conclusive evidence that it's the main benefit is actually getting an early weed kill with either a chemical fallow or cutting for hay, or not so much grazing. So it's a multi-system benefit thing. You've got some nitrogen input. If you've cut it for hay and removed it, you've lost a lot of the nutrients anyway. But certainly weed control is a big issue, big part of that story.
And what we've often found too is it's not necessarily about what grows above too. It's because what grows above, the residues, goes into that pool which feeds the microbes. The roots that grow below are often the ones that contribute to the soil organic carbon that we measure, because they have harder to break down substance. The suberin of the roots stops the decomposition. So the amount of roots you can grow is probably also a factor into what you might consider growing. So a shallow rooted legume may not be as good as something that has a lot more branching, or something that might stick around a bit longer too. So the root structure is important to think about.
But I guess, Amanda, as well, just having that diversity in the system. So keeping the vetch or something, keeping a legume within your farming system is obviously going to be of so much benefit than not.
Definitely.
So if vetch was the one that worked for you, then...
Oh, yeah, we've had lots of different things. We've looked at chickpeas, lentils, so there's been lots of different. So it depends on what grows well. So really you just want the plant that's suited, the legume that's suited to grow well in your area. The more cover we have, the less decomposition, the less moisture we're losing. So it's all about getting back to your ground cover. How much you're growing above and how much you're growing below ground will all impact what your soil carbon is.
The person who asked that question is just called attending. So if they do want to reach out and we can provide information from BCG's previous research around that topic as well. One from our own internal staff member, Kate Madden, is that in terms of making sure we're putting back what we take off in grain in terms of nutrients, do you have any good resources that are available to provide that information?
So I reckon Rob would have been one of the key players in this field, and there's some really, really good resources around to demonstrate what how much nutrients how much offtake there is with each crop. But Rob, your space.
I can certainly share some of the things that we've done over the journey, and probably phosphorus has been one of the big things, and the whole nutrient composition of materials. Certainly, I can share that with you, Tom, and you can share it back through the BCG networks.
Yeah, well, if there's resources available, we can put that on our website too. Rob, jump on, who's listening, to just go to bcg.org.au, and we'll try and get it in the next couple of days. And then Kate's also asked if the replacement strategy will mean the crop will always have nutrients required to meet its potential. So we know that obviously crops are water limited environment, need those nutrients to meet their yield potential. Is there a replacement strategy that we're looking at, Cassie, or is there something better we can be doing?
I reckon that you want to be running the two in parallel. So you want to be looking at your soil tests and what you've got in reserve, and you want to see kind of look at your yield potential, what targets you're aiming for, and see how much you need to add. But I think the very kind of basic gross mass balances still have a role to play in contexting, because if and look, even for the nutrients that we don't tend to account for every season, so a lot of the micronutrients and come into this, and even like maybe potassium to some degree, but maybe not. But even looking at if you know that you're pulling off so much every year, you're saying, well, even if I don't get a profitable yield response from the addition of that nutrient into my system, if I know that every few years I'm just putting a bit of micronutrients and a bit other stuff back in that I've taken out, then I know that I'm not going to get into that environment where they start to impact on soil function and plant growth. So it's almost like taking care of things before they become an issue, and just to make sure that they're adequate.
The other aspect is that some soils have their own nutrient requirements. So a high P-fixing soil, like calcium carbonate soil, for example, or very acidic aluminium and iron soil, will have a phosphorus demand just like a plant. So you need to meet that phosphorus demand. So your replacement value has to include some sort of soil, for taxation. Same occurs with potassium. Potassium soils have a potassium demand. Plants and nitrogen has a demand into organic matter, as well as losses to the environment. So, certainly starting with an idea of removal gives you a starting point, but you need to monitor after that to make sure that, what tax is being charged by the soil in addition to the materials that are being removed.
And then with that, Rob, I guess where the nutrient removal theory breaks down is if you're coming from a period of low rainfall years, and you're saying, I've only been taking off this much, then you hit a big rainfall year and your system can't capitalize on that.
Absolutely.
Then that's when that starts to break down. But I think it's probably worth having that just as a check to make sure, at the bare minimum, that what you're adding and what you're doing is in excess of what you're is above what you've taken off.
It comes back to your initial point, Cassie, at the very start of this presentation, is that it comes down to making sure that you are undertaking the soil tests that are required to understand. You don't measure it, you can't manage it, you can't understand where you're starting from in order to replace those nutrients that have been lost to the system or to the plant.
Yeah.
We've got a couple more. What are the major cations that are being exported, Cassie, and what's the best way to replace them?
Well, the key one obviously is calcium, and mag, and then you got some potassium and sulfur as well. Sorry, potassium and sodium. So the key aspects are, if you're adding lime to the system to ameliorate any acidity, then you'll be pulling that calcium. You'll be putting that calcium back into the system anyway. Soils with a higher CEC, obviously have more cations there to draw from, but I'd say that's probably of lower. So if you're getting into a point where your cations are depleting, then you're probably acidifying as well. I'm not sure if that's a key point to focus on, or if it's worth kind of looking at the bigger picture as well, just noting that there are those cations moving out. But Rob, what would your thoughts be?
I think the issue is cations in some ways, I don't like to say this, but some ways incidental to the main nutrients that you're dealing with. In terms of cations, for a lot of us, it's really about making sure that soil structure with exchangeable sodium percentage, for example, is on song, and getting the major nutrients right. If you're acidified the soil, then you have to apply calcium, magnesium, as dolomite or limestone. The amounts are small on an incremental, but over an incremental period, they do get quite large. So a tonne or so. You know, most crops, there's calculations about most crops about what the line requirement to grow a tonne of wheat is. And I can't remember the number.
Yeah,
But
we've got the numbers, Tom. We can send that through. Yeah,
absolutely. We can add that to the list of resources on our website as well, Cassie, for attendees. We'll move on. We've got a few still coming in, but I might ask if we can halt the questions now as we're running a bit. But in terms of standing stubble versus stubble on importance, is there a difference whether or not it's standing or rolled or anything like that from the general point of view of the panel?
Standing stubble just makes it a bit easier for trafficability.
Sowing that
rather than having stubble on the ground. You know, some concept was that about if stubble was rolled into the ground, you know, you'd cause it to break down quicker. That might be true too, I don't know, but also slashing stubble and getting on the ground. But I think the main thing is about standing stubble is trash flow.
Yeah.
And erosion risk.
And erosion risk, thanks, yeah.
Yeah, and so I guess then we'll move on to the next one. In terms of getting nutrient into the crop then or into the soil, a couple of different questions on it, so we'll sort of cover off on both. But what's the best way to incorporate those sort of bulk products? Is putting it down the boot while sowing a decent method of incorporating things like lime or other nutrients? Is it disturbance with a knife point to incorporate it, or is it cultivated across a paddock?
So unfortunately, disturbance by sowing just isn't doing the trick. Because if it was, we'd be in a lot better position than what we are at the moment with our soil acidity. Certainly, I guess the key rule of thumb that I try and work on is incorporate to the depth that you need, but only within what that soil can cope with. So, and obviously erosion risk and everything comes into play with all this. But if we think about that, we used to broadcast our lime and then not expect to see any value of it for 3 or 5 years. But if we incorporate that lime, we see an instant response. So we get a growth benefit from that in that first year in acid soils. It really seems to say that some form of incorporation, ideally more than incorporation by sowing, is best. But what I try and work on is manage that within your system. So if you say, well, I need to apply lime, so I need to incorporate, what part of the rotation can I do that to actually give some benefit to it and less risk? So it might be that you incorporate, you broadcast your lime in March, or you can incorporate, whenever you can, and then you incorporate your stubble almost prior to sowing, and then you sow you go for your early seeding crops after that. Probably your cereals are a bit easier because they can deal with a bit more soil disturbance if the seed bed isn't as good as it should be. And obviously trafficability is an issue as well. So really kind of plan it out to make it fit your system. And the idea that we're working on as well is rather than fairy dusting lime across a large area, kind of just doing a bit just to make you feel better that you've put some on. If you need to apply lime, apply a higher rate. So actually try and get up to 5.8 is now the target in a lot of areas to make sure that you stay above where you need to be for a long time and to stop ongoing subsoil acidification. So sounds like a horrible number, but the idea is you do that once and then your maintenance then is less ongoing or is basically the same ongoing. So idea is that if you've got a set budget for lime, which everyone has set, they can only spend so much, spend what you can in that budget, but put that higher rate on a smaller area and do it properly. And then you don't have to come back to that area for a long time. So it's like that one-off strategic tillage event. And as much as no-till is amazing, this is just one area that the cracks are appearing. So do it once. If you can time that after a rain event to pull up, to pick up a weed germination event as well. So that's one spray pass that you're not doing. If there's a few ways that you can stack that tillage event up so it actually adds value to the system and resets, and then you go again into no-till. And we know that that has completely minimal value on soil carbon over the long term. And because you're amending your soil pH to greater depth, that in fact increases your soil carbon potential within that greater depth because you've ameliorated that acidity.
I just want to throw a caution in there. Before you start worrying too much about lime in the Wimmera and Mallee, make sure you go and do your soil pH test, because our soils really are 7 to 8.5. And so that at the moment, liming is not something you consider. But certainly monitor your soil pH. And then it would, except for a couple of situations, mainly a leached out sandhill, you might need some lime, but don't necessarily take that as being a recommendation to use lime in the Wimmera and Mallee.
No, it's really specific areas, Rob. So around Mount Arapiles, we're finding acidities coming through really strongly, and some of those areas south and east of Horsham. But certainly as you head north, it's not really a big deal. But yeah, get your pH test done, and then if they're good, at least then you know that's where you stand.
So we've got a question here, Cassie, around, again, resources for deciding nutrient application for the soil without having to rely on an agronomist recommendation. You, BCG, just reach out with your soil test once they're done, and there's people around who can provide those recommendations. That one, BCG do our soil program as well. So if you want to reach out to us, we're happy to give you the advice.
Yeah, if you're not trusting the agronomist you're working with, I think you need to change your agronomist. An agronomist should be a partner in your business, not someone who's trying to flog. If your view is that an agronomist is someone trying to flog your stuff, then go to a different agronomist, because they should be working as a knowledgeable partner with you, rather than a salesman coming in.
And just to explain to your agronomist or you're looking for that advice from, is that this is a strategy implement on your farm.
Yeah.
So I'd like to try more than just a replacement. We want the soil function. So yeah, work together. And like Rob said, they're meant to help you with your business, not to do with it. It's your farm at the end of the day. A final one before we clock off for the afternoon. There are various groups around that seem to be saying that it's possible to grow good crops with no fungal pesticides by adding microbes from a drum, with a disc, growing roots all year round to keep the soil healthy, etc. The panel's general view on those types of advocates, I suppose, around reducing fungal pesticides. Obviously a good thing to do if you can, but yeah, general thoughts, I suppose, without getting too far into it.
Sounds too good to be true.
Amanda?
I think it would be wonderful if we could get to that. I'm not sure how we go from where we generally are to getting to that. And I know people are trying it. So I'm very much following a lot of people who are going through the system and following what's happening. So I'm more in the gathering more information and seeing what happens. But I'm not quite sure how it goes. And I don't want anyone restricting being able to put on fungicides or insecticides or doing what they need to do if things occur. So it's that being able to respond as you need to for your system.
There is a case especially with insecticides and those broad spectrums, and understanding thresholds for what you're trying to manage, knowing what beneficial bugs you've got out there. There is an opportunity you don't have to, other than that tool is still available if things get. Try those integrated pest management strategies. Work with your to understand what your thresholds are. So, and then even with now that things like blackleg and canola, you can, if it starts after a certain point, you don't have a yield loss. So just understanding those thresholds. Maybe that prophylactic use of insecticides and fungicides is not a good thing, but monitoring, understanding what the issues are and using things sparingly to get the best result. And in terms of growing roots all year round, it's just a difficult thing in a water limited environment.
And the other thing, Tom, is that we still need to be replacing the nutrients that we're taking out. So you still, as the challenge we've got is some of these systems go really well initially when they come off at the back of good banks of nutrition and stuff in soil. So then, first year or so things look pretty good, and then if you're not supporting the soil and sustaining that soil by replacing what you're removing, then obviously you're in the downhill spiral. There's been the whole cover cropping thing is a completely different story, which we obviously can't go into because we're out of time. Just to flag that a lot of the discussions around risk. If you're growing plants all year round, then what does that mean in terms of your cash crop's ability to bring home a water limited yield potential? And how much if you're depleting your soil moisture storage over summer, which we know that a lot of the cover crops that are used with really good evidence to show they actually drain soil water down to 60 centimetres. What does that mean in terms of your ability to manage your in-season crop and bring that home? There's some interesting good things coming from cover crops around how the role that they could play in infiltration capacity, so sort of recharge potential in soil. But that's very site specific, and we don't have some really good data sets in Australia around that kind of thing. And the other thing is everything becomes so much more complex around managing your disease and weed pressures and stuff, because you're introducing more elements of plants in the system. Green bridging becomes a real concern. What's the downstream impacts that come from that in future? So certainly happy to keep an open mind, learn from farmers that are trying these things, and I think with time we'll end up sort of creating an Australian centric version of what that kind of system might look like.
Again, there's no such thing as the perfect system, because all microbes and insects and so forth and weeds are very adaptable, and as soon as there's a gap in a system, they'll fill it. I mean, that's why you've got spiders in the corner of your room. Not you specifically, Cassie, but they occupy a niche that is there, and that's what happens in any biological system. And so there'll be no perfect system. We'll just have to keep adapting to the challenges that come up. Every new challenge will require a new system.
And as new things come through, we can then assess those as tools in our system. We don't have to wed to a philosophy or an approach over the long term, or we look at something, we assess it. Does that fit? Can that add value? Does that complement what I'm doing? If it does, well, give it a shot. If it doesn't, don't go for it just because it sounds amazing.
Look for the data. Look for the repetition. Understand if it's going to work. Guys, we've gone over time, but it's been really informative this morning, and the discussion I think has been really good. For listening in live, there will be a second session on this topic on Tuesday next week, 8 o'clock, as long as we can all get up and get going. We're discussing more of those practical applications for soil management and organic carbon. So if you are available next week and you haven't registered, there should be a link available. If there's not a link available, reach out to me at BCG to register, and we'll see you next week.